Chapter 15. Prospects. Centuries from now, superstring theory, or its evolution within M-theory, may have developed so far beyond our current formulation that it might be unrecognizable even to today's leading researchers. As we continue to seek the ultimate theory, we may well find that string theory is but one of many pivotal steps on a path toward a far grander conception of the cosmos, a conception that involves ideas that differ radically from anything we have previously encountered. The history of science teaches us that each time we think that we have it all figured out, nature has a radical surprise in store for us that requires significant and sometimes drastic changes in how we think the world works. Then again, in a bit of brash posturing, we can also imagine, as others before us have perhaps naively done, that we are living through a landmark period in humanity's history in which the search for the ultimate laws of the universe will finally draw to a close. As Edward Whitton has said, I feel that we are so close with string theory that, in my moments of greatest optimism, I imagine that any day, the final form of the theory might drop out of the sky and land in someone's lap. But more realistically, I feel that we are now in the process of constructing a much deeper theory than anything we have had before, and that well into the 21st century. When I am too old to have any useful thoughts on the subject, younger physicists will have to decide whether we have in fact found the final theory. 1. Although we are still feeling the aftershocks of the second superstring revolution and absorbing the panoply of new insights that it has engendered, most string theorists agree that it will likely take a third and maybe a fourth such theoretical upheaval before the full power of string theory is unleashed and its possible role as the final theory assessed. As we have seen, string theory has already painted a remarkable new picture of how the universe works, but there are significant hurdles and loose ends that will no doubt be the primary focus of string theorists in the 21st century. And so, in this last chapter, we will not be able to finish telling the story of humanity's search for the deepest laws of the universe, because the search continues. Instead, let's guide our gaze into the future of string theory by discussing 5 central questions string theorists will face as they continue the pursuit of the ultimate theory. What is the fundamental principle underlying string theory? One overarching lesson we have learned during the past 100 years is that the known laws of physics are associated with principles of symmetry. Special relativity is based on the symmetry embodied in the principle of relativity, the symmetry between all constant velocity vantage points. The gravitational force, as embodied in the general theory of relativity, is based on the equivalence principle, the extension of the principle of relativity to embrace all possible vantage points, regardless of the complexity of their states of motion. And the strong, weak, and electromagnetic forces are based on the more abstract gauge symmetry principles. Physicists, as we have discussed, tend to elevate symmetry principles to a place of prominence by putting them squarely on the pedestal of explanation. Gravity, in this view, exists in order that all possible observational vantage points are on completely equal footing, i.e., so that the equivalence principle holds. Similarly, the non-gravitational forces exist in order that nature respect their associated gauge symmetries. Of course, this approach shifts the question of why a certain force exists to why nature respects its associated symmetry principle. But this certainly feels like progress, especially when the symmetry in question is one that seems eminently natural. For example, why should one observer's frame of reference be treated differently from another's? It seems far more natural for the laws of the universe to treat all observational vantage points equally. This is accomplished through the equivalence principle and the introduction of gravity into the structure of the cosmos. Although it requires some mathematical background to appreciate fully, as we indicated in Chapter 5, there is a similar rationale behind the gauge symmetries underlying the 3 non-gravitational forces. String theory takes us down another notch on the scale of explanatory depth because all of these symmetry principles, as well as another, supersymmetry, emerge from its structure. In fact, had history followed a different course, and had physicists come upon string theory some 100 years earlier, we can imagine that these symmetry principles would have all been discovered by studying its properties. But bear in mind that whereas the equivalence principle gives us some understanding of why gravity exists, and the gauge symmetries give us some sense of why the non-gravitational forces exist, in the context of string theory, these symmetries are consequences. Although their importance is in no way diminished, they are part of the end product of a much larger theoretical structure. This discussion brings the following question into sharp relief. Is string theory itself an inevitable consequence of some broader principle, possibly but not necessarily a symmetry principle, in much the same way that the equivalence principle inexorably leads to general relativity, or that gauge symmetries lead to the non-gravitational forces? As of this writing, no one has any insight into the answer to this question. To appreciate its importance, we need only imagine Einstein trying to formulate general relativity without having had the happy thought he experienced in the Berne Patent Office in 1907 that led him to the principle of equivalence. It would not have been impossible to formulate general relativity without first having this key insight, but it certainly would have been extremely difficult. The equivalence principle provides a succinct, systematic, and powerful organizational framework for analyzing the gravitational force. The description of general relativity we gave in Chapter 3, for example, relied centrally on the equivalence principle, and its role in the full mathematical formalism of the theory is even more crucial. Currently, string theorists are in a position analogous to an Einstein bereft of the equivalence principle. Since Veneziano's insightful guess in 1968, the theory has been pieced together, discovery by discovery, revolution by revolution, but a central organizing principle that embraces these discoveries and all other features of the theory within one overarching and systematic framework, a framework that makes the existence of each individual ingredient absolutely inevitable, is still missing. The discovery of this principle would mark a pivotal moment in the development of string theory, as it would likely expose the theory's inner workings with unforeseen clarity. There is, of course, no guarantee that such a fundamental principle exists, but the evolution of physics during the last 100 years encourages string theorists to have high hopes that it does. As we look to the next stage in the development of string theory, finding its principle of inevitability, that underlying idea from which the whole theory necessarily springs forth, is of the highest priority. 2. What are space and time, really, and can we do without them? In many of the preceding chapters, we have freely made use of the concepts of space and of space-time. In Chapter 2, we described Einstein's realization that space and time are inextricably interwoven by the unexpected fact that an object's motion through space has an influence on its passage through time. In Chapter 3, we deepened our understanding of space-time's role in the unfolding of the cosmos through general relativity, which shows that the detailed shape of the space-time fabric communicates the force of gravity from one place to another. The violent quantum undulations in the microscopic structure of the fabric, as discussed in Chapters 4 and 5, establish the need for a new theory, leading us to string theory. And finally, in a number of the chapters that followed, we have seen that string theory proclaims that the universe has many more dimensions than we are aware of, some of which are curled up into tiny but complicated shapes that can undergo wondrous transformations in which their fabric punctures, tears, and then repairs itself. Through graphic representations such as figures 3.4, 3.6, and 8.10, we have tried to illustrate these ideas by envisioning the fabric of space and space-time as if it were somewhat like a piece of material out of which the universe is tailored. These images have considerable explanatory power. They are used regularly by physicists as a visual guide in their own technical work. Although staring at figures such as the ones just mentioned gives a gradual impression of meaning, one can still be left asking, what do we really mean by the fabric of the universe? This is a profound question that has, in one form or another, been the subject of debate for hundreds of years. Newton declared space and time to be eternal and immutable ingredients in the makeup of the cosmos, pristine structures lying beyond the bounds of question and explanation. As he wrote in the Principia, absolute space, in its own nature without relation to anything external, remains always similar and immovable. Absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external. Gottfried Leibniz and others vociferously disagreed, claiming that space and time are merely bookkeeping devices for conveniently summarizing relationships between objects and events within the universe. The location of an object in space and in time has meaning only in comparison with another. Space and time are the vocabulary of these relations, but nothing more. Although Newton's view, supported by his experimentally successful 3 laws of motion, held sway for more than 200 years, Leibniz's conception, further developed by the Austrian physicist Ernst Mach, is much closer to our current picture. As we have seen, Einstein's special and general theories of relativity firmly did away with the concept of an absolute and universal notion of space and time. But we can still ask whether the geometrical model of space-time that plays such a pivotal role in general relativity and in string theory is solely a convenient shorthand for the spatial and temporal relations between various locations, or whether we should view ourselves as truly being embedded in something when we refer to our immersion within the space-time fabric. Although we are heading into speculative territory, string theory does suggest an answer to this question. The graviton, the smallest bundle of gravitational force, is one particular pattern of string vibration, and just as an electromagnetic field such as visible light is composed of an enormous number of photons, a gravitational field is composed of an enormous number of gravitons, that is, an enormous number of strings executing the graviton vibrational pattern. Gravitational fields, in turn, are encoded in the warping of the space-time fabric, and hence we are led to identify the fabric of space-time itself with a colossal number of strings all undergoing the same, orderly graviton pattern of vibration. In the language of the field, such an enormous organized array of similarly vibrating strings is known as a coherent state of strings. It's a rather poetic image, the strings of string theory as the threads of the space-time fabric, but we should note that its rigorous meaning has yet to be worked out completely. Nevertheless, describing the space-time fabric in this string-stitched form does lead us to contemplate the following question. An ordinary piece of fabric is the end product of someone having carefully woven together individual threads, the raw material of common textiles. Similarly, we can ask ourselves whether there is a raw precursor to the fabric of space-time, a configuration of the strings of the cosmic fabric in which they have not yet coalesced into the organized form that we recognize as space-time. Notice that it is somewhat inaccurate to picture this state as a jumbled mass of individual vibrating strings that have yet to stitch themselves together into an ordered whole because, in our usual way of thinking, this presupposes a notion of both space and time. The space in which a string vibrates and the progression of time that allows us to follow its changes in shape from one moment to the next. But in the raw state, before the strings that make up the cosmic fabric engage in the orderly, coherent vibrational dance we are discussing, there is no realization of space or time. Even our language is too coarse to handle these ideas, for, in fact, there is even no notion of before. In a sense, it's as if individual strings are shards of space and time, and only when they appropriately undergo sympathetic vibrations do the conventional notions of space and time emerge. Imagining such a structureless, primal state of existence, one in which there is no notion of space or time as we know it, pushes most people's powers of comprehension to their limit. It certainly pushes mine. Like the Stephen Wright one-liner about the photographer who is obsessed with getting a close-up shot of the horizon, we run up against a clash of paradigms when we try to envision a universe that is, but that somehow does not invoke the concepts of space or time. Nevertheless, it is likely that we will need to come to terms with such ideas and understand their implementation before we can fully assess string theory. The reason is that our present formulation of string theory presupposes the existence of space and time within which strings, and the other ingredients found in M theory, move about and vibrate. This allows us to deduce the physical properties of string theory in a universe with one time dimension, a certain number of extended space dimensions, usually taken to be 3, and additional dimensions that are curled up into one of the shapes allowed by the equations of the theory. But this is somewhat like assessing an artist's creative talent by requiring that she work from a paint-by-number kit. She will undoubtedly add a personal flair here or there, but by so tightly constraining the format of her work, we are blinding ourselves to all but a slender view of her abilities. Similarly, since the triumph of string theory is its natural incorporation of quantum mechanics and gravity, and since gravity is bound up with the form of space and time, we should not constrain the theory by forcing it to operate within an already existing space-time framework. Rather, just as we should allow our artist to work from a blank canvas, we should allow string theory to create its own space-time arena by starting in a spaceless and timeless configuration. The hope is that from this blank slate starting point, possibly in an era that existed before the Big Bang or the pre-Big Bang, if we can use temporal terms for lack of any other linguistic framework, the theory will describe a universe that evolves to a form in which a background of coherent string vibrations emerges, yielding the conventional notions of space and time. Such a framework, if realized, would show that space, time, and by association dimension are not essential defining elements of the universe. Rather, they are convenient notions that emerge from a more basic, atavistic, and primary state. Already cutting-edge research on aspects of M-theory, spearheaded by Stephen Schenker, Edward Witten, Tom Banks, Willy Fischler, Leonard Susskind and others too numerous to name, has shown that something known as a zero brane, possibly the most fundamental ingredient in M-theory, an object that behaves somewhat like a point particle at large distances, but has drastically different properties at short ones, may give us a glimpse of the spaceless and timeless realm. Their work has revealed that whereas strings show us that conventional notions of space cease to have relevance below the Planck scale, the zero branes give essentially the same conclusion but also provide a tiny window on the new unconventional framework that takes over. Studies with these zero branes indicate that ordinary geometry is replaced by something known as non-commutative geometry, an area of mathematics developed in large part by the French mathematician Alain Connes. 4. In this geometrical framework, the conventional notions of space and of distance between points melt away, leaving us in a vastly different conceptual landscape. Nevertheless, as we focus our attention on scales larger than the Planck length, physicists have shown that our conventional notion of space does re-emerge. It is likely that the framework of non-commutative geometry is still some significant steps away from the blank slate state anticipated above. But it does give us a hint of what the more complete framework for incorporating space and time may involve. Finding the correct mathematical apparatus for formulating string theory without recourse to a pre-existing notion of space and time is one of the most important issues facing string theorists. An understanding of how space and time emerge would take us a huge step closer to answering the crucial question of which geometrical form actually does emerge. Will string theory lead to a reformulation of quantum mechanics? The universe is governed by the principles of quantum mechanics to fantastic accuracy. Even so, in formulating theories over the past half-century, physicists have followed a strategy that, structurally speaking, places quantum mechanics in a somewhat secondary position. In devising theories, physicists often start by working in a purely classical language that ignores quantum probabilities, wave functions, and so forth. A language that would be perfectly intelligible to physicists in the age of Maxwell and even in the age of Newton, and then subsequently overlaying quantum concepts upon the classical framework. This approach is not particularly surprising, since it directly mirrors our experiences. At first blush, the universe appears to be governed by laws rooted in classical concepts, such as a particle having a definite position and a definite velocity at any given moment in time. It is only after detailed microscopic scrutiny that we realize that we must modify such familiar classical ideas. Our process of discovery has gone from a classical framework to one that is modified by quantum revelations, and this progression is echoed in the way that physicists, to this day, go about constructing their theories. This is certainly the case with string theory. The mathematical formalism describing string theory begins with equations that describe the motion of a tiny, infinitely thin piece of classical thread. Equations that, to a large extent, Newton could have written down some 300 years ago. These equations are then quantized, that is, in a systematic manner developed by physicists over the course of more than 50 years. The classical equations are converted into a quantum mechanical framework in which probabilities, uncertainty, quantum jitters, and so on are directly incorporated. In fact, in Chapter 12 we have seen this procedure in action. The loop processes, see Figure 12.6, incorporate quantum concepts. In this case, the momentary quantum mechanical creation of virtual string pairs, with the number of loops determining the precision with which quantum mechanical effects are accounted for. The strategy of beginning with a theoretical description that is classical and then subsequently including the features of quantum mechanics has been extremely fruitful for many years. It underlies, for example, the standard model of particle physics. But it is possible, and there is growing evidence that it is likely that this method is too conservative for dealing with theories that are as far-reaching as string theory and M-theory. The reason is that once we realize that the universe is governed by quantum mechanical principles, our theories really should be quantum mechanical from the start. We have successfully gotten away with starting from a classical perspective until now, because we have not been probing the universe at a deep enough level for this coarse approach to mislead us. but with the depth of string/M theory, we may well have come to the end of the line for this battle-tested strategy. We can find specific evidence for this by reconsidering some of the insights emerging from the second superstring revolution, as summarized, for example, by Figure 12.11. As we discussed in Chapter 12, the dualities underlying the unity of the 5-string theories show us that physical processes that occur in any one-string formulation can be reinterpreted in the dual language of any of the others. This rephrasing will at first appear to have little to do with the original description, but in fact, this is simply the power of duality at work. Through duality, one physical process can be described in a number of vastly different ways. These results are both subtle and remarkable, but we have not yet mentioned what may well be their most important feature. The duality translations often take a process described in one of the 5-string theories that is strongly dependent on quantum mechanics, for example, a process involving string interactions that would not happen if the world were governed by classical, as opposed to quantum physics, and reformulate it as a process that is weakly dependent on quantum mechanics from the perspective of one of the other string theories, for example, a process whose detailed numerical properties are influenced by quantum considerations, but whose qualitative form is similar to what it would be in a purely classical world. This means that quantum mechanics is thoroughly intertwined within the duality symmetries underlying string/M theory. They are inherently quantum mechanical symmetries, since one of the dual descriptions is strongly influenced by quantum considerations. This indicates forcefully that the complete formulation of string/M theory, a formulation that fundamentally incorporates the newfound duality symmetries, cannot begin classically and then undergo quantization in the traditional mold. A classical starting point will necessarily omit the duality symmetries, since they hold true only when quantum mechanics is taken into account. Rather, it appears that the complete formulation of string-M theory must break the traditional mold and spring into existence as a full-fledged quantum mechanical theory. Currently, no one knows how to do this, but many string theorists foresee a reformulation of how quantum principles are incorporated into our theoretical description of the universe as the next major upheaval in our understanding. For example, as Kumran Vafa has said, "I think that a reformulation of quantum mechanics which will resolve many of its puzzles is just around the corner." I think many share the view that the recently uncovered dualities point toward a new, more geometrical framework for quantum mechanics, in which space, time, and quantum properties will be inseparably joined together. 5. And according to Edward Witten, I believe the logical status of quantum mechanics is going to change in a manner that is similar to the way that the logical status of gravity changed when Einstein discovered the equivalence principle. This process is far from complete with quantum mechanics, but I think that people will one day look back on our epoch as the period when it began. 6. With guarded optimism, we can envision that a reframing of the principles of quantum mechanics within string theory may yield a more powerful formalism that is capable of giving us an answer to the question of how the universe began and why there are such things as space and time, a formalism that will take us one step closer to answering Leibniz's question of why there is something rather than nothing. Can string theory be experimentally tested? Among the many features of string theory that we have discussed in the preceding chapters, the following 3 are perhaps the most important ones to keep firmly in mind. First, gravity and quantum mechanics are part and parcel of how the universe works, and therefore any purported unified theory must incorporate both. String theory accomplishes this. Second, studies by physicists over the past century have revealed that there are other key ideas, many of which have been experimentally confirmed, that appear central to our understanding of the universe. These include the concepts of spin, the family structure of matter particles, messenger particles, gauge symmetry, the equivalence principle, symmetry breaking, and supersymmetry, to name a few. All of these concepts emerge naturally from string theory. Third, unlike more conventional theories such as the Standard Model, which has 19 free parameters that can be adjusted to ensure agreement with experimental measurements, string theory has no adjustable parameters. In principle, its implications should be thoroughly definitive. They should provide an unambiguous test of whether the theory is right or wrong. The road from this in-principle ratiocination to an in-practice fact is encumbered by many hurdles. In Chapter 9, we described some of the technical obstacles, such as determining the form of the extra dimensions that currently stand in our way. In Chapters 12 and 13, We placed these and other obstacles in the broader context of our need for an exact understanding of string theory, which, as we have seen, naturally leads us to the consideration of M-theory. No doubt achieving a full understanding of strings M-theory will require a great deal of hard work and an equal amount of ingenuity. At every step of the way, string theorists have sought and will continue to seek experimentally observable consequences of the theory. We must not lose sight of the long-shot possibilities for finding evidence of string theory discussed in Chapter 9. Furthermore, as our understanding deepens, there will, no doubt, be other rare processes or features of string theory that will suggest yet other indirect experimental signatures. But most notably, the confirmation of supersymmetry through the discovery of superpartner particles as discussed in Chapter 9 would be a major milestone for string theory. We recall that supersymmetry was discovered in the course of theoretical investigations of string theory, and that it is a central part of the theory. Its experimental confirmation would be a compelling, albeit circumstantial, piece of evidence for strings. Moreover, finding the superpartner particles would provide a welcome challenge, since the discovery of supersymmetry would do far more than merely answer the yes-no question of its relevance to our world. The masses and charges of the superpartner particles would reveal the detailed way in which supersymmetry is incorporated into the laws of nature. String theorists would then face the challenge of seeing whether this implementation can be fully realized or explained by string theory. Of course, we can be even more optimistic and hope that within the next decade, before the Large Hadron Collider in Geneva comes online, the understanding of string theory will have progressed sufficiently for detailed predictions about the superpartners to be made prior to their hoped-for discovery. Confirmation of such predictions would be a monumental moment in the history of science. Are there limits to explanation? Explaining everything, even in the circumscribed sense of understanding all aspects of the forces and the elementary constituents of the universe, is one of the greatest challenges science has ever faced. And for the first time, superstring theory gives us a framework that appears to have sufficient depth to meet the challenge. But will we ever realize the promise of the theory fully and, for example, calculate the masses of the quarks or the strength of the electromagnetic force, numbers whose precise values dictate so much about the universe? As in the previous sections, we will have to surmount numerous theoretical hurdles on the way to these goals. Currently, the most prominent is achieving a full, non-perturbative formulation of string/M theory. But is it possible that even if we had an exact understanding of string/M theory, framed within a new and far more transparent formulation of quantum mechanics, we could still fail in our quest to calculate particle masses and force strength? Is it possible that we would still have to resort to experimental measurements rather than theoretical calculations for their values? And moreover, might it be that this failing does not mean that we need to look for an even deeper theory, but simply reflects that there is no explanation for these observed properties of reality? One immediate answer to all these questions is yes. As Einstein said some time ago, the most incomprehensible thing about the universe is that it is comprehensible. 7. The astonishment at our ability to understand the universe at all is easily lost sight of in an age of rapid and impressive progress. However, maybe there is a limit to comprehensibility. Maybe we have to accept that, after reaching the deepest possible level of understanding science can offer, there will nevertheless be aspects of the universe that remain unexplained. Maybe we will have to accept that certain features of the universe are the way they are because of happenstance, accident, or divine choice. The success of the scientific method in the past has encouraged us to think that with enough time and effort, we can unravel nature's mysteries. But hitting the absolute limit of scientific explanation, not a technological obstacle or the current but progressing edge of human understanding, would be a singular event, one for which past experience could not prepare us. Although of great relevance to our quest for the ultimate theory, this is an issue we cannot yet resolve. Indeed, the possibility that there are limits to scientific explanation in the broad way we have stated it is an issue that may never be resolved. We have seen, for instance, that even the speculative notion of the multiverse, which at first sight appears to present a definite limit to scientific explanation, can be dealt with by dreaming up equally speculative theories that, at least in principle, can restore predictive power. One highlight emerging from these considerations is the role of cosmology in determining the implications of an ultimate theory. As we have discussed, superstring cosmology is a young field, even by the youthful standards set by string theory itself. It will, undoubtedly, be an area of primary research focus for years to come, and it is likely to be one of the major growth areas of the field. As we continue to gain new insight into the properties of string/M theory, our ability to assess the cosmological implications of this rich attempt at a unified theory will become ever sharper. It is possible, of course, that such studies may one day convince us that, indeed, there is a limit to scientific explanation, but it is also possible, to the contrary, that they will usher in a new era, an era in which we can declare that a fundamental explanation of the universe has finally been found, reaching for the stars. Although we are technologically bound to the Earth and its immediate neighbors in the solar system, through the power of thought and experiment we have probed the far reaches of both inner and outer space. During the last 100 years in particular, the collective effort of numerous physicists has revealed some of nature's best-kept secrets. And once revealed, these explanatory gems have opened vistas on a world we thought we knew, but whose splendor we had not even come close to imagining. One measure of the depth of a physical theory is the extent to which it poses serious challenges to aspects of our worldview that had previously seemed immutable. By this measure, quantum mechanics and the theories of relativity are deep beyond anyone's wildest expectations. Wave functions, probabilities, quantum tunneling, the ceaseless roiling energy fluctuations of the vacuum, the smearing together of space and time, the relative nature of simultaneity, the warping of the space-time fabric, black holes, the Big Bang. Who could have guessed that the intuitive, mechanical, clockwork Newtonian perspective would turn out to be so thoroughly parochial that there was a whole new mind-boggling world lying just beneath the surface of things as they are ordinarily experienced? But even these paradigm-shaking discoveries are only part of a larger, all-encompassing story. With solid faith that laws of the large and the small should fit together into a coherent whole, physicists are relentlessly hunting down the elusive unified theory. The search is not over, but through superstring theory and its evolution into M theory, a cogent framework for merging quantum mechanics, general relativity, and the strong, weak, and electromagnetic forces has finally emerged. And the challenges these developments pose to our previous way of seeing the world are monumental. Loops of strings and oscillating globules, uniting all of creation into vibrational patterns that are meticulously executed in a universe with numerous hidden dimensions capable of undergoing extreme contortions in which their spatial fabric tears apart and then repairs itself. Who could have guessed that the merging of gravity and quantum mechanics into a unified theory of all matter and all forces would yield such a revolution in our understanding of how the universe works? No doubt, there are even grander surprises in store for us as we continue to seek a full and calculationally tractable understanding of superstring theory. Already through studies in M theory, we have seen glimpses of a strange new domain of the universe lurking beneath the Planck length, possibly one in which there is no notion of time or space. At the opposite extreme, we have also seen that our universe may merely be one of the innumerable frothing bubbles on the surface of a vast and turbulent cosmic ocean called the multiverse. These ideas are at the current edge of speculation, but they may presage the next leap in our understanding of the universe. As we fix our sight on the future and anticipate all the wonders yet in store for us, we should also reflect back and marvel at the journey we have taken so far. The search for the fundamental laws of the universe is a distinctly human drama, one that has stretched the mind and enriched the spirit. Einstein's vivid description of his own quest to understand gravity, the years of anxious searching in the dark, with their intense longing, their alternations of confidence and exhaustion, and final emergence into the light 8, encompasses surely the whole human struggle. We are all, each in our own way, seekers of the truth, and we each long for an answer to why we are here. As we collectively scale the mountain of explanation, each generation stands firmly on the shoulders of the previous, bravely reaching for the peak. Whether any of our descendants will ever take in the view from the summit and gaze out on the vast and elegant universe with a perspective of infinite clarity, we cannot predict. But as each generation climbs a little higher, we realize Jacob Bronowski's pronouncement that, in every age there is a turning point, a new way of seeing and asserting the coherence of the world. 9. And as our generation marvels at our new view of the universe, our new way of asserting the world's coherence. We are fulfilling our part, contributing our rung to the human ladder, reaching for the stars. Albert Einstein, a name synonymous with genius, harbored a dream. He envisioned a universe governed by a single, elegant theory. This unified field theory would weave together all the fundamental forces of nature. Gravity, electromagnetism, and the nuclear forces would all flow from one beautiful set of equations. Einstein spent decades chasing this dream. He tirelessly searched for the mathematical framework that would unify these seemingly disparate forces. He yearned to reveal the hidden connections within the fabric of the universe. Despite his relentless efforts, the unified theory remained elusive. The universe, it seemed, was reluctant to reveal its deepest secrets. Still, Einstein's dream inspired generations of physicists to continue the quest for a unified understanding of the cosmos. Einstein's quest for unification was hindered by the limited knowledge of his time. The world of physics was very different then. Scientists were only beginning to unravel the mysteries of the atomic nucleus. The strong and weak nuclear forces, crucial for a unified theory, were still shrouded in mystery. Without a complete understanding of these fundamental forces, Einstein's dream remained tantalizingly out of reach. His equations, though revolutionary, couldn't quite bridge the gap between gravity and the other forces. The tools and knowledge needed to delve deeper into the heart of matter were yet to be developed. Einstein, despite his brilliance, was limited by the scientific landscape of his era. However, his pursuit laid the groundwork for future physicists to pick up the torch and continue the search. The decades following Einstein's era witnessed a revolution in physics. Quantum mechanics, a groundbreaking theory, emerged to explain the bizarre behavior of particles at the subatomic level. Scientists peered deeper into the atom, discovering a zoo of new particles and forces. This new understanding of the quantum world provided crucial missing pieces to the puzzle of unification. Physicists realized that a unified theory would need to reconcile Einstein's theory of gravity with the strange and counterintuitive world of quantum mechanics. This realization led to the development of string theory, a radical new approach to understanding the universe at its most fundamental level. String theory offered a fresh perspective, suggesting that everything in the universe is made up of tiny vibrating strings. Imagine a world where the tiniest building blocks aren't point-like particles, but rather minuscule vibrating strings. This is the essence of string theory. Just like a violin string playing different notes, these strings vibrate in different patterns, giving rise to the particles and forces we observe. Superstring theory, an extension of string theory, takes this idea a step further. It incorporates the concept of supersymmetry, which suggests that every known particle has a superpartner particle. This symmetry helps to tame some of the mathematical inconsistencies that plagued earlier versions of string theory. Superstring theory offers an elegant and potentially unifying framework for understanding the universe. It has the potential to explain not just the particles and forces we know, but also the very fabric of space-time itself. One of the most mind-bending aspects of string theory is the existence of extraspatial dimensions. These dimensions extend beyond the familiar three-dimensional space we navigate daily. We experience the world in three dimensions of space: up, down, left, right, forward, backward, and one dimension of time. This four-dimensional space-time forms the stage on which all physical phenomena play out. However, string theory suggests that the universe might have more spatial dimensions curled up and hidden from our view. These additional dimensions could be compactified, existing at scales so small that they elude direct detection. These extra dimensions are not some science fiction fantasy but a mathematical consequence of string theory. The equations that describe string theory inherently require these additional dimensions for consistency and to unify the fundamental forces of nature. Just as a garden hose may appear as a one-dimensional line from a distance but reveals its two-dimensional surface upon closer inspection, these extra dimensions are hidden within the fabric of our universe. They are compactified in such a way that they are only noticeable at incredibly small scales. These extra dimensions are hidden within the fabric of our universe. They are intricately woven into the very structure of space-time, influencing the fundamental properties of particles and forces. These hidden dimensions, though invisible to us, could hold the key to understanding some of the universe's most profound mysteries, including the nature of gravity and the unification of forces. They might provide insights into why gravity is so much weaker compared to other fundamental forces, including the nature of gravity and the unification of forces. The existence of these dimensions could explain phenomena that current theories struggle to account for, such as the behavior of black holes in the early moments of the Big Bang. They represent a realm beyond our perception, a hidden landscape that challenges our understanding of reality. Exploring these dimensions could revolutionize our grasp of the cosmos, a realm where the very fabric of space-time is woven together in ways we are only beginning to comprehend. As we delve deeper into the mysteries of string theory, we may uncover the secrets of these hidden dimensions and their profound impact on our universe. Visualizing extra dimensions can be a challenge. These dimensions are not something we encounter in our everyday lives, making them difficult to comprehend. Our brains are wired to perceive the world in 3 spatial dimensions. This is how we navigate our environment, understand space, and interact with objects around us. However, we can use analogies to grasp this mind-bending concept. Analogies help bridge the gap between the familiar and the unknown, making complex ideas more accessible. Imagine a tightrope walker moving along a rope. To the walker, the rope is a narrow path with limited movement options. From a distance, the tightrope appears as a one-dimensional line. It seems like a simple, straight path with no depth or width. The tightrope walker can only move forward or backward. Their movement is restricted to this single dimension, much like how we perceive our 3-dimensional world. However, a tiny ant crawling on the rope experiences an additional dimension. To the ant, the rope is not just a line, but a surface it can explore. It can also move around the circumference of the rope, a dimension hidden from the distant observer. This additional movement is imperceptible to the tightrope walker. Similarly, the extra dimensions proposed by string theory are curled up and hidden from our macroscopic view. These dimensions are compactified, existing in ways that are not immediately visible to us. They exist at incredibly small scales, billionths of a billionth of a meter, far smaller than anything we can currently observe. These scales are beyond the reach of our most powerful microscopes and scientific instruments. Yet, these hidden dimensions could have profound implications for our understanding of the universe. They might hold the key to unifying the forces of nature, explaining the fundamental structure of reality, and unlocking new realms of physics we have yet to explore. The quest for a unified theory is driven by a deep-seated human desire to find order and harmony in the universe. Superstring theory, with its elegant framework of vibrating strings and hidden dimensions, offers a tantalizing glimpse into this hidden harmony. The beauty of string theory lies in its potential to unify all of physics into a single, coherent framework. It suggests that the seemingly disparate forces and particles that make up our universe are merely different manifestations of the same fundamental entity, vibrating strings. This vision of the universe, though still speculative, is profoundly inspiring. It suggests that beneath the surface complexity of the cosmos lies a deep and elegant simplicity, a symphony of strings vibrating in harmony. Despite its elegance, string theory is still a work in progress. It faces significant challenges, both theoretical and experimental. One of the biggest hurdles is finding ways to test the theory's predictions. The incredibly small scales at which string theory operates make it difficult to design experiments that can directly probe these realms. However, physicists are developing ingenious new methods and technologies to push the boundaries of observation. The quest to unify the forces of nature and unravel the mysteries of the universe is a journey of exploration and discovery. It is a journey that pushes the boundaries of human knowledge and challenges us to expand our understanding of the cosmos and our place within it. The search for a unified theory is ultimately a search for ourselves. It is a journey that transcends the boundaries of science and philosophy, touching the very essence of what it means to be human. It is a quest to understand the fundamental laws that govern our existence and the nature of reality itself. This pursuit drives us to explore the deepest questions and the most intricate details of the cosmos. Whether or not string theory proves to be the ultimate theory of everything, it has already profoundly impacted our understanding of the universe. It has opened new avenues of thought, and has challenged our perceptions of space, time, and matter. It has revealed a universe stranger and more wondrous than we could have imagined, a cosmos filled with phenomena that defy our conventional understanding. A universe of hidden dimensions, vibrating strings, and unseen forces that weave the fabric of reality, and a deep underlying unity that connects all things, from the smallest particles to the vast expanses of space. As we continue to explore the cosmos and delve deeper into the heart of matter, we uncover layers of complexity and beauty that inspire awe and wonder. We are constantly reminded of the elegance, beauty, and mystery that surrounds us. Each discovery, each new piece of the puzzle brings us closer to understanding the grand tapestry of the universe. The universe is an endless source of wonder and inspiration, a boundless expanse that invites us to dream and to explore. And our quest to understand it is a testament to the power of human curiosity and the indomitable spirit of exploration. It is a journey that unites us, driving us to push the boundaries of knowledge and to seek answers to the most profound questions of existence.